All right, let's start. Today it's going to be a problem from biology, which is really one of the key problems to study, namely how do bacteria manage to swim up chemical gradients. That's called chemotaxis. And if I'm not really transparent today, it's because I just came back from the US this morning, so hope I don't make too many mistakes. If I do, please help me along. Here I showed you that, right? This is a run-and-tumble motion of bacteria. And you see these bacteria, they run, then they kind of stop, they tumble. And with the tumble events, there's also a reorganization of the flagella. That means those extensions of the bacteria that self-propel the bacteria. And if you coarse-grain, we talked about this, then you roughly have two states of those bacteria. One state is where they show counterclockwise motion of the flagella. That's when they run with a certain speed, v0. And the other one is where these flagella are rotating clockwise, then they don't organize that well, and you have a tumble event where the bacterium basically stands still. And then if you look at the motion, it's this alternation between run and tumble events. Now, what's the physics at that scale? You have to imagine these bacteria are just very small. They are a few microns or a micron in length. And then the fluid in which they are swimming feels very differently from you swimming in a pool. And the point is that the Reynolds number that they experience is very, very small. For a human, it's about 100. For these bacteria, the Reynolds number is 10 to the minus 6. And that means these bacteria are really in a highly damped medium, and that means their motion is overdamped. You can completely ignore any kind of inertial effects. Now, how they switch back and forth, that's due to an internal biochemical reaction network. I will talk about this a bit, but we don't really focus on the details of this reaction network. And if you want to read more about it, I will guide you to some interesting literature about the chemosensory system of these bacteria. So why is that cool, and what's the challenges if you study chemotaxis? Well, one challenge is really what is the limit of sensing and navigation under the influence of noise, because this organism, as I said, is very small and it has to sense gradients in a way which is a stochastic measurement and not a deterministic type of measurements, as you will see. Another question I'm not going to talk about, but it's very interesting. It is about the thermodynamics of sensing and adaptation. And here the question is, what are the energetic and informational costs of chemotactic behavior? That's an ongoing research topic in the field. And last, and that's something I will touch upon again, is how you go actually from the single cell motion to collective motion. So what's the population dynamics, and how do individuals act together to form some emergent behavior? So let's talk first a bit about the chemosensory system. And don't be scared, I'm making it very simple and only touch upon things which are important for us. So here you have the cell membrane. On the outside, you may have some signals, some chemicals. And those chemicals, they are sensed by these sensory chemoreceptors that you have here, which are included in the membrane. And once they sense that there is some kind of chemoattractant in the surroundings, they'll change the behavior or the state of this protein here that's called key A. Key stands for chemotaxis, and A, etc., just enumerates the different proteins. This key A is a quite important protein. It's a kinase, and that means it can actually use the ATP hydrolysis and transfer a phosphate to a other protein, which is called key Y. So by doing so, by transferring the phosphate to the key Y, it's switching this other protein from a kind of inactive state here to an active state where the phosphate is attached. And only in this active state, it will then activate the flagellar motor and switch it from clockwise to counterclockwise motion. So you have a kind of a sequence of sensing, activating, switching a key Y into the active state, and then activating the motor protein. In that cycle, he has other proteins that I didn't discuss, and these other proteins are important for making the adaptation, the chemosensory system such that it can adapt to different kind of gradients in a very efficient way. If you want to read about this, I'll refer you to this paper here, which is a very nice review article from which I also took this figure. Okay, so for us, it's a stochastic sensory system, and we would like to have a coarse-grained view where we have this in the background and then model really what's going on with an individual bacterium. All right, so let me stop here and go to the board. So what I would like to discuss with you is the following. So we do have this chemosensory system, and the important protein is this phosphorylated HYP, and that then switches the motor activity between clockwise and counterclockwise. Okay? And that's all we need for doing the analysis. And for simplicity, and that's really just for simplicity, because you will see that this already gives you the major insights into the behavior. For simplicity, we will assume that the motion that we have is just one-dimensional motion. And then when you look at the time scales, the run is about, I think, a second, and the tumble events, they are about a tenth of a second. And what we will assume is that these tumble events are instantaneous. So all we model is that our bacterium is either moving to the right or it's moving to the left. And I call this here +1 and -1, that's moving to the right. And this here is moving to the left. And the switching between the two, moving to the right and to the left, is by rates. So the rates that we have is alpha plus, which may depend on position. And this rate alpha plus gives you a transition from sigma, so let me call this here sigma, equal +1, so right moving, to -1, and alpha minus of x is you start from a left moving bacterium and it transitions to a right moving bacterium. Okay, so that's the model, a very simple model, 1D, and it's a jump process between right and left moving. And when it's moving a certain direction, right, so if it's moving here in the plus direction, it will have the velocity v0, and it's moving in the left direction, it has the velocity minus v0. And that's a constant because it's internal property of the flagella that are attached to the bacteria. All right, so how would we now describe that in terms of a stochastic model? So we take as quantities p plus or minus of x and t, which is the probability that the bacterium is moving right or left equal plus or minus. Okay. Now, what's the corresponding Chapman-Kolmogorov equation? Well, we have to now take our knowledge that we acquired over the last lectures and put it into practice. This is a process that is a jump process. And at the same time, if the particle is in a certain state, like plus or minus, it moves at a constant speed. So it has only drift during that time. And that means for the plus motion, this will have a drift in the forward direction. And that's the term we have. There's no diffusion term here because we assume that this is moving at a constant speed. And then if there is an event that switches with a rate alpha plus, then you lose bacteria from that plus state, and they go into the minus state, and vice versa. If these bacteria switch from left moving to right moving with rate alpha minus, you gain in the state of the right moving bacteria. And similarly for the motion in the minus direction, though to the left, this is now with a velocity minus v naught, which gives a plus v naught in the drift term, dx p minus of t, and then just the opposite. So this is here going to be a, well, I can write it this way, minus alpha minus of x, p minus of p of x and t, plus alpha plus of x, p plus of x and t. Okay, so those terms here that correspond to the switching reaction, they of course cancel because one's gain is the other one's loss. All right, that's the equation that we would like to analyze. And now let's coarse grain this even a bit more than what we have here. And for that, let's say that it's instructive to look at the total density, or meaning the total probability density, which is the sum of our bacteria moving to the right and to the left. You can think of this as the total probability density, that's what it is. But you can also think of that as the density of your bacteria. The other quantity that I want to write down, which has an immediate interpretation in terms of the physics, is the current. And the current, net current, is the difference between the probabilities moving to the right and to the left, multiplied by the corresponding transport velocity, which is v naught. So that's v naught times the difference between the forward and backward moving bacteria. Okay. All right, what's the equations for the quantities that we just wrote down? So the equation for the total density, just look at this equation, you sum them up, the reaction terms cancel. So this is just a term that depends on the first two terms that you have here. And that exactly is the current, right? So this is minus dx j of x and t. And that should be clear because particles have to obey a conservation law, and that's what you have here. There was a question?
You have a t on the left, right?
Yeah, sorry, I do mean that. Yeah. So this is the temporal change of probability density. It has to be conserved. And when you think about this as particle density, it has also to be conserved because you don't lose or gain any particles. Okay, that's our first equation. So we do have a conservation law for the total density. What about the equation for the current? So let's just write it out, and then just algebra, and I write it down for you, and then we interpret the terms one by one. So mathematically, this is what you get. You get a sum of 3 terms, and they are of the following form. Okay. Now, what do they mean? So this term here is the gradient of the density or probability density times V naught squared. That looks like a current that's analogous to Fick's law. So it's a diffusive current because of the flipping of directions back and forth. That's diffusion. Because of jumping, right? Because of jumping back and forth. Now this here is you lose current in the sense that this current relaxes, again, because of flipping back and forth. So that's I call a damping term of the persistence of our current. Well, and this one is clear. This is just a drift. Sorry, I did something wrong here. There should be a minus. This is the drift term because of the asymmetry in the forward and the backward motion. So if they are the same, there's no drift. But if alpha minus is distinct from alpha plus, you will get a drift term. So you have diffusion, damping of persistence, and drift. In general, you would need to solve these 2 equations together. Okay. But we can simplify. We can simplify because we know that there's different time scales that play a role in these dynamics of a chemotactic system. Let's look at the time scales. So there's one time scale, which is the time during which you have a run. So tau run. And we talked about this. Runtime is a second. Then we also have another time, which is a diffusion time. And diffusion time now means if you look at the motion of such a bacterium, if you look at over long time scales, it looks like flipping back and forth very fast. So that means you have an effective diffusion of this bacterium. So that means there will be a diffusion time, but what's the diffusion coefficient for that? You can kind of read it off here. So this is a Fick's law. So the diffusion coefficient will be proportional to the velocity squared. And to make things right, there needs to be a time scale because that's a just meter squared per second squared. So you need another time scale, and that means you can just estimate that this here will be scaling as the velocity squared divided by the tumbling rate, and then you have the right units of meter squared per second. So that means there will be a diffusive time scale on which systems equilibrate in the sense that you have a steady state distribution, and there will be a length scale, and this length scale I'll talk about in a minute. So we'll have a diffusive time scale being a length scale squared divided by an effective diffusion coefficient. So this is just a standard diffusion law. You can read it from here to the left, L squared goes like effective diffusion coefficient times the time, and just inverting that. So that's the typical diffusion time. Runtime and diffusion time with this effective diffusion coefficient. What's the length scale I should think about? Well, if you look into the system and ask what's the typical run length, right? This run length will be the velocity of our particle times the run time. So V naught times tau run, because that you can measure the velocity is something like 20 micrometer per second. This will be of the order of 20 micrometer. That means during a run, the bacteria will typically run 20 micrometer. Now, in order for me to be able to actually have a homogeneous or some kind of continuous profile in P, there needs to be many runs back and forth. So the length scale should be many of this runtime. I can put here an arbitrary number. Let's say the length should be at least something like 100 micron that I should use in order to calculate a typical diffusion time. Well, and now if you just plug in all these numbers, the time for diffusion will turn out to be 25 seconds. Okay? And that you have to compare with this runtime that you have here. So this runtime is very, very short as compared to the time you have the equilibration of diffusive motion, and you get some homogeneous density profile. Right? And that means if you look now at these terms here in the current is flipping back and forth between the two states. That will equilibrate on the time scale that you have the temporal evolution of the density because of this time scale separation. Okay, so because of that, we can do an adiabatic assumption saying that on the relevant time scale, we are interested in the time evolution of the density has equilibrated. So dTj is 0. And that means now this is 0, so I can actually write the current in terms of the other terms that we have there. Okay, so that means in this adiabatic approximation, the effective current in the stationary state will have two terms. One is minus V naught squared over alpha plus alpha minus dxp. Right, and this is what I've been talking about before. This is a diffusive current with an effective diffusion coefficient B given by the velocity squared divided by the rates. And the second term is V naught. And now you have the difference between the rates, and here you have the sum of the rates times P. So we have diffusion and we have drift. And that means, in summary, as we collect all these terms, the effective coarse-grained dynamics on a time scale that's much larger than the tumble time is a drift diffusion equation. Okay. So we can write this also as minus d effective times dxp plus V effective times P. The important point to note is that these are not constants. The effective drift velocity and the effective diffusion coefficient that you see here, they depend on the quantities here on the top. V naught is constant, but these rates of switching back and forth between forward and backward motion, they are depending on position. So in general, both of them will be functions of position. Right? And then as you combine this, right, you'd get a Fokker-Planck equation with diffusion and drift. I'm not going to write it down because basically just insert the current that we have now on the board in the continuity equation, which is this equation here, and then you get this drift diffusion Fokker-Planck equation. All right, so far so good. We didn't really talk about yet what is alpha plus of x and alpha minus of x. How should we think of this? How are they related to the sensory system that we have? So how related to the sensory system? And that's a big question, because here you would need, and I'm not going to do this, show or derive how the sensory system reads off the chemical gradients and how this internal machinery of all the proteins, HeA, HeY, etc., transforms this external signal into an action on the molecular motor. Okay? And the action is you switch between directions of motion here, forward and backward. And there's many ways this could happen, right? And it turns out, and this is an insight from the field, that the sensing that you have is temporal sensing. Just imagine you have these gradients, they are shallow maybe, right? And these bacteria are just a micron in length. What do they measure? Do they measure the actual gradient of the profile, but for that they would need to move around to actually see the gradient? Or do they just read off the temporal change of the density along their trajectory? And that's what they do. They read off the temporal change of the chemical density. So let's see of x equal the chemoattractant or repellent density. Then what they read off is the change of this gradient along their own trajectory, which is x of t. All right, so now let's calculate what dc dt is and just use the chain rule. dc dt is d dt of c of x of t then, right? And this is x dot times gradient of c, and our x dot is the velocity v naught times sigma of t, which is whether you're moving to the right or to the left. So as you insert this here, this is equal to v naught times sigma of t dx of t, dx of the concentration of your external chemoattractant. So we assume now that it measures exactly this and write down expressions for the switching rate based on the knowledge in the field that this is a temporal sensing. So let us write this down. You have some kind of basal rate that I call alpha naught. And then, let me write it down. You have 1 minus or plus chi v naught dxc. Right, so I'm basically writing here what I found here on the top. It's sensing ddt, and I'm rewriting ddt in this form that we wrote down here. So what does that mean? If it's moving up in the forward direction, then given the gradient in the forward direction, which increases with increasing x, it reduces, therefore the minus, the rate to switch back. So if you're moving the right direction, you keep on going, you don't switch back. If you go the wrong direction, which is in the minus direction, you increase your rate of flipping in the other direction. Okay? So that's what we basically assume to be the case for the sensing mechanism in these bacteria. So once you have that assumption, you can now calculate from that to linear order in those gradients the effective velocity, drift velocity, and the effective diffusion coefficient. So all you do is you insert that expression here into relation for the effective diffusion coefficient and the effective drift velocity. For the diffusion coefficient, you have in the denominator alpha plus plus alpha minus, and you see to leading order, the gradients just cancel out. So that means to leading order in the gradients, the effective diffusion coefficient is given by V naught squared divided by 2 times alpha naught. And that should not surprise us, because that's basically what you will get from a dimensional argument saying that diffusion coefficients have to have units of meter squared per time. It's a constant, right? This is a position-independent diffusion coefficient. And the contrast comes here when you write down the effective drift velocity, because there you have the difference between the forward and the backward rate. So the gradient doesn't cancel out. The gradient actually sums up. And what you get is chi times V naught squared over 2 alpha naught times the gradient of C of x. And that's now a nice result, because it says the velocity is given by the sensitivity, this chi parameter, then the effective diffusion coefficient, V naught squared over 2 alpha naught, times the gradient of the concentration. That means, in summary, the velocity, the drift velocity, will move up the gradient. Okay? So this really means bacteria move up the gradient by this very simple and basic mechanism that you flip back and forth, and you make your flipping rate dependent on the chemoattractant concentration, so you do temporal sensing. Questions? Right. Okay, that's a basic insight. Now, let me turn to something else. Let us now ask what if, and that's in general the case, you have not C of x, but you actually have C of x and t. So the chemical concentration is not given externally, fixed, but it's varying in time. And in many cases, the bacteria actually are responsible by themselves to create those gradients. So they produce some chemicals, some chemoattractants themselves, and then move in their own gradients. Okay? So let's write that down. Let's say that the concentration that we have of these chemicals is such that the chemicals, as they must, of course, they are molecules, they will diffuse in space with their own diffusion coefficient, dc, that's the diffusion coefficient for the chemicals. And of course, they don't live forever, so there is some degradation of these chemicals with some rate k. And they are produced, and let's say I'm just writing here an arbitrary function f of rho. So the bacteria in some way produce the chemoattractants. The simplest you can write down, so e.g. f of rho could just be alpha of rho. You could have other forms. This could saturate because alpha rho means the more bacteria you have, the more you actually produce. But there are saturation effects, so this may have a different functional form. Okay. So you have a chemical. The chemical diffuses, it's degrading, and there's production by the bacteria themselves, where I also changed notation now. So instead of rho, instead of p, I'm writing rho, because in the end, if you coarse-grain, the probability density is analogous to an actual particle density. You had a question? Just answer. Yeah, okay. So this replacement here is not quite exact, because the density is a fluctuating variable. It's a field, and the probability density is a variable which is a continuous function. It's not fluctuating. But for our purpose, let's just take this point of view, because it's easier to argue in terms of densities than to argue in terms of probability densities. So what would be the replacement for our effective drift velocity? So remember, this was chi times v naught squared over 2 alpha naught times the gradient of c. Okay? That was our result that we had, deriving it from this spontaneous switching model. So let's generalize that now. Let's say this chi is not just a constant. It may be a function of the concentration itself. And here it comes in that you have to actually worry about how is the sensing mechanism of these bacteria actually working. What does it sense in detail? And how does it read off in detail the concentration field? Okay, and the different biochemical models that you can come up with. And for us, let's just do a phenomenological description and say it's some function of concentration. And, well, then I have the gradient in C of x, but the C of x is now a function not just of position, but also of time. What that means, if I write out the equation, you have the density of our bacteria showing a drift term which has this form of coupling to the concentration field times the density, right? This is how we couple. And we do have a diffusion term, and here I'll just leave out the index effective rho of x and t. So and once you have that equation, this is a very famous and classic equation from the field. These are known as Keller-Segel models. And they have a very, very broad mathematical literature where people study the mathematical properties of those, not just in one dimension, because you can just change your derivative to a gradient, and then this is still a very well-defined set of equations. Okay? So it's a partial differential equation with drift and diffusion, and you would like to know what kind of behavior does it actually have. Okay, and let me show you before we go into the break. All right, so here is such an equation. So just different names here now. Instead of rho and c, this uses the symbols u and v, because that's basically from the math literature where this is the typical variables you choose. So here we have the term that I've been talking about. You have some diffusion term for this density here of of the bacteria. Then you have here a drift term, and then here you have an additional reaction term that's included here, and here you have again the diffusion of your chemicals, and another term that comes from the reactions that we just talked about. Okay, that's the mathematical structure. I took this from a web page, and where you can actually simulate this in an interactive way. So let's just go to that web page. That's the simulation you see. So these are the patterns that come out. It's actually the pattern of the bacterial density here, and you see this is a labyrinth-like pattern that forms. And this is not the only pattern. There are many, many different patterns this system shows. And when you go to the website, and I think Toby sent around the corresponding information, you can play with the parameters and then see that this Keller-Segel model shows all kinds of beautiful phenomena. I can't show it here because I can't at the same time hold it up and change parameters, but during the break, you're welcome to look at that. All right. Questions before we break? Yeah, please.
Do people also try pattern information analysis with foam-like structure?
Of course, of course. So if you have these partial differential equations, so as we have them here, those partial differential equations, they have a variety of solutions. You can ask, given a homogeneous state where rho and c are constant, is that homogeneous state stable to fluctuations? And then that's called a linear stability analysis, and you can calculate the spectrum. And from the spectrum then infer under what conditions a homogeneous state is unstable. And that gives you a phase diagram of when patterns are forming in principle. Once you have patterns forming, then you may have different patterns, as we saw. And analyzing those different patterns and what the time scales and length scales, etc., is, that's actually a very challenging problem, because you need to calculate nonlinear behavior and not just a linear spectrum. Okay. Other questions?
I was just thinking, how to get to the expression of V expected again?
This one here?
Yes, like the line above the row. Yeah, and V effective is equal, no, that's the line effective. It's equal to this chi,
chi of c, so some function, times the gradient. So I'm just generalizing the result I derived from before. This is the simplified analysis where I just say they flip back and forth in a fixed gradient, and the sensing is temporal sensing. And now I'm saying I take a step forward, a leap of faith, and say if I were to understand more in detail how the chemosensing works, I could then calculate a response function, a sensitivity function, chi of c, that characterizes the response of the bacteria to the chemoattractant or chemorepellent field.
So it's similar, it's like a more refined version of this alpha minus alpha plus.
Yeah, it's a more refined version, and there are different options for what you can take here. So the simplest would be just saying that it's a constant. So we could go back and say chi equals chi naught. This is what we derived. But there are also other models where it has been shown that chi of c can also have the form of a constant 1 over 1 plus c over c naught, and many other forms. And it's actually a problem that you can study by looking at the reaction network. What kind of form would you calculate given your knowledge about the reaction network in detail?
And the same would probably go for the f of rho.
Same thing.
In the other direction.
Same thing. So this is actually easier because there you just have to specify what happens to the production of the chemoattractant. And the most basic assumption really is that the density, the bacteria themselves, they produce the chemoattractant with a certain rate, which is alpha. And then you can say, okay, there's some limitation to that production because they don't have infinite resources. It can't be linear in rho all the time. If you go above a threshold in bacterial density, you just saturate at some point in the production of chemoattractant that you can have.
And just as a follow-up, you said there's a little caveat between rho and p.
Okay, I will come to this later in the lecture. For now, P, right, is a probability density. It's described by a Fokker-Planck equation. And it's the time evolution of that probability density. When I would really discuss the density of bacteria, I'm not talking about one bacterium, but about many of them, right? And these many bacteria, if I think of them as a density, and have the bacteria here in a certain radius, then of course their number is not constant. The density is itself a fluctuating variable. So if I really want to write down an equation of motion for the physical density of bacteria, I would need to write down something like a Langevin equation for that density. Okay?
So it's something like the expected density?
Yeah, that's what you should. Yeah, that's what you should think. It's the expected density, the mean. Yeah, the expected density. That's the best way of saying it.
Okay.
Yeah, and it doesn't really matter that much here, the distinction between p and rho. I just switched to rho because I thought your intuition for that would be better than for a probability density. Yeah. All right, so let's have a break.